Good afternoon, all of you, and thank you for coming here to attend my defense. The title of my presentation is Graphene-Based Nanostructured Materials for Electrochemical Energy Storage. I want you to imagine a world where you don't have to pay for electricity. Maybe you can make money by selling electricity which is generated by solar cells which are installed on the roof of your house. Maybe you own a self-driving electric automobile. Such ideas have already been conceptualized, and it's just a matter of time when this becomes a reality. Of course, we need a lot of technological advancement. One such important technological advancement is in the field of energy storage. With the rise of renewable energy and the intermittent nature of solar energy and wind energy, a lot of focus has recently been put upon the electrochemical energy storage devices. Lithium-ion batteries are the current market leader in electrochemical energy storage because they have very high specific energy. That means they can store a large amount of energy in a small mass. However, they have very small specific power. The region here represents electrochemical capacitors which can deliver high specific power but have low specific energy. Now, researchers in both of these fields want to reach to the area of high specific energy and high specific power. But not only that, we want our devices to be low cost and safe. Now, Department of Energy suggests that there are four major broad areas where we need to do research to make innovative energy storage systems. I am particularly interested in graphene-based nanostructured materials. Specifically, I want to understand at fundamental level, at molecular level, to tailor the nanostructured electrodes with targeted properties. So, as I said, I'm highly interested in graphene because graphene, as many call it, super material and wonder material because of its unique properties such as very high specific surface area. It has very high intrinsic mobility, which makes it one of the best electrical conductors on Earth. So graphene has just not applications in the field of energy storage, but also in the fields of flexible electronics, catalysis, paintings, and coatings. However, bulk production of graphene through an inexpensive and safe way is not possible yet, and hence it poses a challenge for its applications to commercialize. However, there is a similar molecule called reduced graphene oxide, which is similar to graphene except that it has few oxygen functional groups and defects on it, can be utilized and has been utilized by researchers to develop applications of graphene. Now, reduced graphene oxide can be made with graphite. Graphite is nothing but stacks of graphene stacked together. Now, to make reduced graphene oxide, we need to exfoliate these layers. We do that by oxidation. Once we oxidize these sheets, they are exfoliated into graphene oxide sheets, which are very well dispersed in water. Now, we need to remove these oxygen functional groups in order to make RGO, and the process is called reduction. It's important to reduce graphene oxide because this material here is insulator. That means it does not conduct electricity. The reason it does not conduct electricity is because in graphene we have free pi electrons which provides its conductivity. However, the pi electrons in graphene oxide are busy in making bonds with oxygen functional groups. So the reduction can be performed in multiple ways. Some of the ways are listed here: photochemical, electrochemical, chemical, and thermal. Now, if this reduction process is not done in a controlled manner, the graphene sheets aggregate together to form this graphite-like structure. This aggregation happens because of the van der Waals attraction forces. Now, although van der Waals forces are weak in nature, but for nanomaterials, they have very high specific surface area, and van der Waals forces add up to become strong, and that's why this aggregation happened. Now, if we started with the graphite and ended with the graphite-like structure, then this will not work. So we need to find a solution to this problem. And when you do literature survey, they say a simple thing. Well, construct unique morphologies and structure graphene-based structures with high electronic conductivity, high surface area, and fast ion transport, and the problem solved. But actually, doing this is very difficult. And the reason is that we lack the fundamental understanding of the process related to graphene oxide and reduced graphene oxide. For example, we do not even understand the georeduction process in its entirety. And partly the reason is because graphene oxide does not have a fixed molecular formula. It is because the formula depends on the sheet size and the degree of oxidation. For the same reason, we also do not understand the chemistry of GO and RGO. Another important aspect is graphene assembly. Now, for graphene assembly is nothing but we need to assemble the 2D nanomaterial into a 3D bulk material which can be utilized into the real applications. So this process is also not very well understood. It's important to know that all these three processes are actually interrelated, because to understand georeduction, you have to understand the chemistry of geo. To make a graphene assembly, of course, you need to convert geo to RGO and then assemble into a graphene-based assembly. So, so these are the major problems with or lack of fundamental understanding. It is important to know that understanding each of these topics will consist of multiple PhDs and many research works. When I started my PhD, my goal was just to work on graphene-based assemblies to make electrochemical capacitors. But throughout my journey, because I had a desire to learn on the related process, I was able to get interesting findings in the field of chemistry of geo and georeduction as well. So, my research is in three parts. So first we'll talk about reduction of graphene oxide, then graphene assembly, and chemistry of geo and RGO. In my first project, I demonstrate the photolytic release of OH free radical from an aqueous dispersion of graphene oxide. In the second project, I actually make 3D graphene frameworks and I study their structure property relationships by investigating fundamental electrochemical properties. And my third project relates to the reactivity of OH free radicals towards RGO and the synthesis of holy graphene using microwave assisted photolysis of H2O2. So let's go to my first project, which is, in this project, I investigate photoreduction of graphene oxide. Now, photoreduction is a sustainable method which is low cost, simple, and does not require any purification step. The results of this research gives an insight in the photostability of graphene oxide and also insights into the photoreduction mechanism. Now, Lurf-Klingowski model is widely accepted structural model of graphene oxide. It suggests that graphene oxides have mainly three kinds of functional groups: carboxylic acid, hydroxyl, and epoxy. Carboxylic acids are normally attached to the edges of the graphene sheets, while epoxy and hydroxyl groups are on the basal plane. Here I show the high resolution TEM images of graphene and graphene oxide. If you see, the green color represents the graphitic region. These are the carbons which are sp2 hybridized in nature and which are responsible for the electrical conductivity of graphene. If you see graphene oxide, most of the area is covered by red, which represents the oxidized carbon with oxygen functional groups, and it is sp3 hybridized, and hence it cannot conduct electricity. Now, of course, we need to do reduction to achieve the conductivity, and we can see these green islands have popped up in reduced graphene oxide, which suggests that this material is now conductive. Now, we perform UV visible spectroscopy on graphene oxide and reduced graphene oxide after photoreduction, and we realize that the absorbance has been increased, and this is actually the characteristics of graphene oxide and reduced graphene oxide. Further, Fourier transform infrared spectroscopy was performed, and here we see that the results actually agree with the literature. Here we see that the graphene oxide has very large OH vibration peak, which completely diminishes in RGO. It suggests that most of the hydroxyl functional groups have been reduced during the photoreduction, and which is plausible because most of the basal plane of graphene oxide has been filled with hydroxyl functional groups. Now, there's a mistake here. In the previous studies for the mechanisms of photoreduction, they suggest that N to pi star transition drives the photochemical reduction. But none of these studies tell anything about the nature of released OH functional groups. So instinctually, after following the FTI results, we suspected that OH free radical might be the product of photoreduction. And to prove that, we utilized a molecule terephthalic acid. So what I mean to say is, if this reaction is true and OH free radical is actually formed, we can react with this OH free radical with terephthalic acid to form 2-hydroxy terephthalic acid. Now this molecule is fluorescent in nature, and we can measure this fluorescence and hence prove that OH free radical is produced in photoreduction. So we did the same thing. So I took graphene oxide and mixed with it terephthalic acid. Then I shined light on it with a xenon lamp. The light consists of UV and visible radiations. Now, graphene oxide should reduce into reduced graphene oxide, and if OH free radicals are formed, it should react with Ta to form TaOH. Then I filter out the RGO, and the remaining solution should be TaOH. So we can know that after doing the fluorescence spectroscopy. So in this experiment, I actually varied the concentration of graphene oxide and also the time of irradiation to understand the effect of concentration and time. Now, in the first graph, I irradiated my graphene oxide and Ta samples for 2 hours, and I varied the concentration. Here I noticed as we increase the concentration, the fluorescence is increased. That means TaOH is actually produced, and the yield of TaOH is increasing as the concentration is increasing. So this proves that OH free radical actually increases with the GO concentration. Now, in the second plot, we irradiated our sample, GO plus Ta sample, for 16 hours. However, the trend changed here. Here, 5 milligram per milliliter concentration show the highest fluorescence. The reason for this was that there was a parasitic light absorption by RGO at high concentration, and hence not all of the GO was able to reduce. So these results actually prove that yes, TaOH was formed, and yes, OH free radical is formed during the photoreduction step. Another thing which we need to keep in mind is whenever designing a photoreduction system is the concentration of GO because of the parasitic light absorption at high concentration. One more experiment we did where we vary the irradiation time by keeping the GO concentration constant, and we realized as the time is increased, OH yield is increased. So this represents kind of the degree of reduction of graphene oxide. So as it is reduced, we get more and more OH free radical. Now after that, we wanted to know whether this photoreduction is caused just by UV spectrum, or visible is also responsible for the photoreduction. So we applied a 400 nanometer pass. What it means is it allows wavelengths only above 400. That is the visible region. So we see, yes, there is a fluorescence. However, this fluorescence is only 20% of the one without any filter. So the extent of reaction is very slow, but it's still there. As of now, it is not clear exactly on the mechanism of photoreduction by visible light, but from this experiments, we actually can prove that yes, visible light can cause the photoreduction. So we wanted to calculate the quantum yield of OH-free radical produced using in photoreduction process. So we employed transient absorption spectroscopy. In transient absorption spectroscopy, a pump light is thrown at the sample, which excites the sample to a higher electronic state, and then a probe light is passed through that sample to find out the absorption of that spectrum. This plot is plotted by absorbance in the excited state minus the absorbance in the ground state. If at the excited state absorption has been increased, we get a positive transient absorption, which is called transient absorption. If after the excitation the absorption is decreased, we get a negative value, which is called transient breach. So we did our experiment where we used graphene oxide, and in another sample we used graphene oxide plus KSCN. Now KSCN is a probe molecule. If OH-free radical is produced, it forms this radical, and it has a unique transient absorption spectra peak at 475 nanometers. This graphene oxide, this is agrees well with the literature. When we added KSCN, we actually saw a peak evolving. That means from this we were able to prove that OH-free radicals are again formed, and we are also able to see the evolution time of the OH-free radical. I have to prepare more on this side. So to move forward, since we were able to prove that OH-free radicals are actually formed, we thought of utilizing these OH-free radicals in environment remediation application. So we took a dye called naphthol blue black, which is an organic dye. We mixed a graphene oxide, dry graphene oxide flake. We put this material in a cuvette and we shine light on it. When we shine light on it, ideally graphene oxide should reduce graphene oxide. So OH-free radicals should attack naphthol blue black because OH-free radicals are highly reactive, and we should see the decrease in the absorption of naphthol blue black, and we actually see the same results. These are the peaks of naphthol blue black, which keeps on decreasing as we shine light on it. Further, to look at it more visually, we mix GO and NBB in a cuvette and shine light on it for 56 hours. And as we see, the blue color of naphthol blue black is disappeared, and the graphene oxide has been reduced and aggregated at the bottom of the cuvette. So this is a demonstration that we can use graphene oxide for environmental remediation, and the separation is also very simple as RGO aggregates in this method. So in summary, we showed that the photolytic evolution of OH-free radical from geodispersion using photoreduction method, and we achieved a high quantum yield of 0.85. We also utilized this method for the environment remediation, and the conversion of GO and RGO during photoanalysis also enables inherent separation from the aqueous dispersion. So this brings us to our second project, in which I developed structure property relationships of self-assembled 3D graphene frameworks. Mainly, I investigate the effect of geosheet size and effect of geo concentration on 3D graphene frameworks. Now, before going into 3D graphene frameworks, I wanted to give a little background on electrochemical capacitors. Electrochemical capacitors work on electric double layer capacitance, where charge storage happens due to the electrostatic interactions. The performance, there are three main performance parameters of a capacitors. First is energy, which is given by half CV square, where C is the capacitance and V is the operating voltage. Power, which is given by V square by 4R, where R is the resistance. And then charging discharging time of the capacitor. Capacitance can also be given by this relationship, where A is the surface area, specific surface area of the electrode. Now, if we need to have high energy, we need to improve the capacitance, and to improve the capacitance, we need to increase the electrode surface area. R is called the equivalent series resistance, which is a combination of different resistance of electrodes, electrolytes, and electrical contacts. So we need to decrease this resistance in order to increase the power. Finally, we want efficient ion diffusion inside our electrodes so that we can have faster charging and discharging. So to test our materials, we use an electrochemical 3-electrode setup, and where our electrode looks, what we call is working electrode, looks like this. We put our sample into a 3-electrode setup where this is working electrode, this is reference electrode, and this is counter electrode, and this is in a KOH electrolyte solution. This is still an incomplete slide. Yeah. So to measure the parameters I showed in the previous slides, we use cyclic voltammetry. In cyclic voltammetry, we sweep the voltage in a cyclic manner and record the corresponding current. For an ideal capacitor, this curve should look like a perfect rectangle. So this is this curve, CV curve, is for a non-ideal capacitor. So capacitance can be calculated from CV using this formula, where I is the current, M is the mass of the electrode, and nu is the scan rate. Further, we will also perform electrochemical impedance spectroscopy, which will be used to determine the various impedances and resistance in our electrochemical system. In an electrochemical impedance spectroscopy, we give our sample, we apply an AC voltage to our sample, and we record the corresponding current so that we can find the values of impedances. So this is a Nyquist plot which we can get from electrochemical impedance spectroscopy. This is the real impedance, this is the imaginary impedance. And from this plot, we are able to determine various